This is the fourth lecture of this series, EPR to quantum communication. Please go through my previous lectures on EPR paradox, quantum entanglement and Bell's theorem. So in this lecture we will discuss about the entanglement as a resource, and we will discuss this quantum teleportation in more detail. The Bell's inequality violation experiments of John Clauser and Alan Aspect opened the eyes of the physics community, and as time progressed, the physics community realized the importance of entanglement as a quantum resource. This quantum resource provided a central ingredient to the rapidly developing field of quantum information science. And the most amazing discovery that the established quantum entanglement as a resource in quantum information processing is this quantum protocol, that is quantum teleportation. And using quantum teleportation, I will show you how to send some unknown state of a quantum system from one place to another place without sending the quantum system itself. So although an arbitrary unknown quantum state cannot be cloned or copied, that comes from no cloning theorem in quantum mechanics, but the unknown state can be sent from one place to another place without sending the system itself. So here the condition applied is that for that we need to share an entangled state between the sender and the receiver. Quantum teleportation protocol was first given in this paper by Charles Bennett et al. Physical Review Later, volume 70, page 1895, 1993, and it was experimentally realized in 1997 by the groups of Anton Zeilinger and Francisco de Martini's groups actually. So I write it down, the references here: Zeilinger et al., Nature 390, volume, page 575, 1997, Nature, and in this Francisco de Martini's et al., Physical Review Later, volume 80, page 1121, 1998. So these are the very first experiments done to verify this quantum teleportation protocol, and I should mention here a recent experiment which was done from satellite actually by the Chinese group. So ground to satellite quantum teleportation by this Chinese group. There are in between many papers, but I am not mentioning all of them, so to be apologize for that. So this one was a breakthrough, I mean using the satellite ground to satellite quantum teleportation by this Chinese group actually, Chinese group. Here I should write down the reference of that paper which was published. The author is Jian Wei Pan et al., published in Nature, which is relatively recent, volume 549, page 70, year 2017. So it is recent paper, right? So that's what I was mentioning here, that recently this ground to satellite quantum teleportation was reported by a Chinese group, where quantum teleportation was achieved for single photon states from a ground station to a low orbit satellite over a distance of up to 1400 kilometers. So yeah, this was the long distance teleportation that was achieved, and this long distance teleportation is important for large scale quantum networks and distributed quantum computation in recent quantum technology. So I will discuss this teleportation protocol in more detail. Okay, so let us now go into the details of quantum teleportation protocol or teleportation scheme. So quantum teleportation protocol is like this. For example, Alice wants to send some quantum information encoded in a state psi. Psi is some state. For example, we consider here two level system, is for example a spin half system. So this psi is some unknown state. So Alice also don't know what is the state actually. That means Alice don't know the values of alpha and beta. So it is a superposition of up and down. They are the eigenstate of the sigma z operator. So we consider it as a two level quantum system, so spin half system. So somehow this a quantum particle, spin half particle is prepared in this state psi, which is of this form, alpha up plus beta down. Now this state is unknown to Alice. That means Alice don't know the values of alpha and beta, and also the situation is like that Alice has access to just only one particle prepared in this state, so she don't have many copies of it. Okay, so under that circumstance, the problem is how Alice can send this information, the quantum information encoded in this two-level system. We call it qubit, two-level quantum system, we call it qubit. So this is a qubit state. So this information Alice want to send from one place to another place at a distance. Here another person called Bob. So Bob is at a distance. So Bob is located at a distance from Alice, and Alice want to send this quantum state to Bob. So one can argue that there is a simple way by which Alice can send this information, this quantum information encoded in this state psi, to Bob, which is at a distance from Alice. What Alice will do, Alice, if Alice knows these values of alpha and beta, what she will do, she will make a phone call to Bob and inform about the values of alpha and beta. Then Bob, what he will do, he will prepare a spin half particle exactly in this state, because he knows the value of alpha and beta. So if he knows the value of alpha and beta, he can prepare the state also at a distance. So by knowing the values of alpha and beta, Alice can send this information in this way by making a phone call to Bob. But here the problem is that Alice also don't know about the values of alpha and beta. So psi, this state psi, is an unknown state, and another restriction is that she has only access to one copy of this state. That means she has only one particle, spin half particle, prepared in that state. Okay, so if she has only one copy of this state, she cannot do that because she don't know about this value, about the values of alpha and beta. So by making a phone call, it doesn't work because Alice don't know about the values of alpha and beta. So Bob cannot prepare the state in prepare a spin half particle in that particular state. Okay, and there is a restriction, there is another restriction for Alice, to know about this quantum state, because as I said that this is an unknown state and she has only one copy of this state psi. She cannot actually know about alpha and beta. There is a no cloning principle in quantum mechanics, so we call it no cloning theorem in quantum mechanics. So I will talk about this no cloning theorem in more detail at the end of this talk. So there is this no cloning theorem. What it says that if we have just one copy of the state and also the state is unknown state, then we cannot make a Xerox copies of this state. So we cannot make many copies of this state. So copying this state is forbidden in quantum mechanics by some unitary operation. So Alice cannot make multiple copy of the same state if she don't know about the state, what exactly the state is. So if Alice could do this, if Alice could copy this state psi, so she could make many copies of the state, and then what she will do, she will make some measurement. Okay, from some measurement statistics she can know about the values of alpha and beta. So one simple strategy will be, what she will do, she will just measure some observable, spin observable. If she has many copies, then she can make repeated measurement, right? It's like she can make many measurement and get some statistics out of there. So for example, she can measure this spin observable sigma z, and finally after doing multiple measurement, because if cloning is possible in quantum mechanics, if cloning would be possible in quantum mechanics, then what she would do, she would make many copies of it and then measure this observable many times and get the statistics out of there. So then this expectation value of this observable sigma z, one can easily calculate. For this state, expectation value will be alpha square minus beta square. For simplicity, I am considering here alpha and beta to be real, and from this sigma z measurement she can actually get this statistics, means this average value of this observable, or the expectation value of this sigma z operator, and which is one can calculate easily from this quantum mechanical expectation value for this state alpha plus beta down, and the result will be this alpha square minus beta square. And if this state is a normalized state, then we will have another equation alpha square plus beta square is equal to 1. So now we can see that we have two unknown values alpha and beta, and we have two equations. So we can easily get the value of alpha and beta from these two equations, equation 1 and equation 2. So this is the fact that if Alice could make multiple copies of the state, even if she don't know about the state, what she will do, she will make many copies of it, and then she will perform some measurements of some observable. Here I have considered this sigma z. I have shown that for this observable she will estimate the average value or the expectation value, which will be this alpha square minus beta square, and from the normalization condition of this state alpha square plus beta square equal to 1, and from these two equations alpha and beta can be estimated by Alice. But in quantum mechanics, I will show you later that because of this no cloning theorem, this operation is not possible, it is forbidden in quantum mechanics. So if Alice has only one copy of an unknown quantum state psi, she cannot actually make many copies of this same state psi, and that's why she will not have these expectation values, because to obtain this expectation value she has to do this measurement many times to estimate the average value. Okay, so because of this no cloning theorem, Alice cannot estimate the value of alpha and beta. So it is not straightforward, I mean by which Alice can send this unknown state information to Bob in this way. For that we need this quantum teleportation protocol, where Alice and Bob should share some entangled state, and then so to do that, actually to send this information, this quantum information about this state psi, what Alice has to do, Alice and Bob, they have to share some entangled state. So what they will do, they will share some entangled state which is prepared by some third party. So quantum teleportation to be successful, what Alice and Bob has to do is, I will show you that they have to share some entangled state. They have to share some entangled state. I will write down the exact expression of that state. So they have to Alice and Bob, they have to share some entangled state, and then so they have to use this quantum resource. This is entangled state. So they have to use this entanglement resource to send this quantum information of this qubit or the qubit state. So by using this entanglement as a resource between Alice and Bob, now Alice can send this information of this state psi to Bob, even if Alice don't know about the values of alpha and beta, that is psi is unknown to psi is completely an unknown state to Alice. Okay, so this portion is not valid operation, so I just erase this portion. This portion is not a valid operation in quantum mechanics because Alice cannot copy this state. So because of this no cloning theorem, which I will talk about in more details at the end of this lecture. So this what I have written over here, this is illegal or this is forbidden. Okay, so this cloning operation is not allowed. So that's why Alice, there is no way that Alice can know about the values of alpha and beta, so that it is not trivial. Alice cannot send this information. Because of that, Alice cannot send this information about this state psi to Bob. Alice cannot send this unknown quantum state to Bob by simply making a phone call. So for that, if Alice has to do it successfully, she has to share some entangled state a priori, I mean beforehand, at the outset they have to share some entangled state like this, two particle entangled state phi AB I have written over here, and they have to use this entangled state as a resource to make it possible. So now Alice can send this information, even if she has only one copy of this state, she can send this information to Bob. Okay, so how she can do it? So now I am going into the details of this teleportation scheme. So I will explain here how Alice can teleport an unknown quantum state to Bob, who is at a distant place there. So suppose Alice wants to send a single qubit unknown quantum state psi prepared in some particle here. So this is an unknown state which Alice wants to send it to Bob. So for quantum teleportation to be successful, Alice and Bob, as I said, they have to share some entangled state. So I name it as phi. Phi is a two particle entangled state shared between Alice and Bob, and this is the unknown state. So we name these particles. So Alice and Bob, they share a two particle entangled state. So this is one particle, this is another particle at a distance. Okay, and we name these particles in this way. This unknown state prepared in this particle, we name it as 1, particle 1, and this spin half particle we name it as 2, and this spin half particle we name it as 3. So altogether we have actually 3 particles. Particle 1 is the spin half system on which this state is prepared, and particle 2 and 3, so this entangled state represent the joint state of these two particles, particle 2 and particle 3. Okay, so altogether we have 3 particles actually, and Alice has access to this particle 1 and 2 in his lab. So Alice is in some lab where she has the access of particle 1 and particle 2. Bob has access to this particle 3 only. So here we have here we name the state of psi and phi in this way. So for this unknown qubit state, we write it as, this is for particle 1, so we write the unknown state psi and we give it the name 1. So psi 1 is actually this unknown state, alpha up plus beta down. So this is the unknown state, the information of which Alice has to send to Bob. Okay, since this is this represents the state of particle 1, we should write here also up 1 and down 1. Okay, and this state, this entangled state between these two particles 2 and 3, so we write it as phi 2 3. So this state is actually, we explicitly write this entangled state. So this is, since this is the joint state of these two particles 2 and 3, and it is an entangled state, and explicitly the state is the maximally entangled state. We consider this maximally entangled state 1 by root 2 up up plus down down. This is one of the Bell state which we have discussed in the first lecture of this series. One can go through that. So there is a tensor product of this between this up state, up state. There is a tensor product actually here and here. So we are not explicitly writing the tensor product over there, but it is implicit. And since this is an entangled state between the particle 2 and 3, and we have named it as phi 2 3, so we should name it here also 2 3 2 3. So these indices are very important. Okay, so the whole system now is a 3 qubit system. So this is 1 qubit, this is second qubit, this is the third qubit, and we can write down the joint state of this whole 3 qubit system also. So that's what we are going to write, the joint state of this whole 3 qubit system. So what is that? So the joint state of the whole 3 qubit system. So I am writing the state of this whole. So we write down it as we name it as capital psi for this whole joint system of 1 2 3 is equal to alpha up 1 plus beta down 1. So this is the state for this particle, and it will be in tensor product with this entangled state phi 2 3. And now, as I already have mentioned that phi 2 3 is my this entangled state, which is a particular Bell state. So, I will just replace this expression of phi 2 3 from here. So, what we obtain is the joint state of this 3 qubit system, that is the joint state of this whole 3 qubit system will be equal to alpha up plus beta down 1 tensor product. This phi 2 3 is this state. So, I write it down explicitly. This is up plus down down. I am not writing down the tensor product here, so it is implicit, and the indices are very important. This is 1 and we should write it here 2 and 3, 2 and 3, because this is the state of particle 2 and 3, that is the joint state of particle 2 and 3, which is an entangled state. So, up to this is very clear that what we have written over here is the joint state of this 3 particle system, where particle 1 is the state of which Alice will send to Bob. So, that is this state particle 1, and particle 2 and 3 are in this entangled state phi 2 3. So, which is a Bell state, up plus down down, 1 by root 2 up plus down down. Okay. So, now we will start from this final expression of this joint 3 qubit system 1 2 3. So, this is capital psi. So, up to now what we have done, we have written down the joint state of this whole system, that is particle 1 2 3 by this capital psi 1 2 3 is equal to alpha up plus beta down, that is the state of this particle, unknown state, tensor product this phi 2 3. Phi 2 3 is an entangled state which is a Bell state. Someone prepared this entangled state phi 2 3. So, someone prepared this entangled state, and then one particle is sent to Alice and another particle was sent to Bob, and in this way actually Alice and Bob is sharing this state phi 2 3. Now, coming back to this joint state of this whole system 1 2 3 represented by this capital psi 1 2 3 in this way. Now, we can actually do the simple linear algebra. We can actually, now we multiply this term by term with this term with the other one. So, what we will get? So, simple linear algebra actually. So, if we do that, what we will get alpha 1 by root 2, alpha by root 2, then we have up. So, we write down this term up 1 and up 2, up 3. This will be the first term, and then we have the second term, this multiplied by the second term of this state. So, that will be alpha 1 by root 2 up 1 and down 2 down 3. So, we are writing it here alpha. So, this plus alpha by root 2 up 1 down 2 down 3, down 2 down 3. Then the next term will be plus this multiplied by this. So, beta 1 by root 2, beta by root 2, here it will be beta by root 2, and then down 1 up 2 up 3. So, this will be down 1 up 2 up 3, up 2 up 3, and there will be fourth term, this multiplied by this term. So, that will be beta 1 by root 2 down 1 down 2 down 3. So, the last term will be beta by root 2 down 1 down 2 down 3, down 2 down 3, and there will be actually tensor product between these states, which we have not explicitly written over here, but there are tensor product here and here and between these different particle states. Okay, but that is implicit, we are not writing it everywhere to keep it simple. So, this is the joint state of this 3 particle system. We have, this is the joint state of this 3 particle system. We have explicitly written down, we have done some simplification, actually this multiplication of this each term, and then we obtain these 4 terms actually. So, then in the next step what we will do, we will focus on this part. of the states. Next, what we will do, we will focus on this part of the state. So this up up, up down, down up, down down. So particle 1, remember that particle 1 is this unknown state, this single qubit state, that is the unknown state, state of which Alice want to send to Bob. Okay, this is the particle 1. Particle 2 and 3 are entangled state. So these indices are very important. So you have to keep track on these indices, otherwise there will be confusion. So that's why I am saying again and again that we should keep in mind the index very carefully. So this is 1, this is 2, this is 3, 1 2 3, 1 2 3, 1 2 3. And now we focus on this first two particle, that is this particle 1 and 2. This part we will focus on these states. Actually we will replace these product states. We will replace these product states as a combination of entangled state between this particle 1 and 2, and we will let us see what happens then. So Alice, and we will remember also, we will keep it in our mind that Alice has access to particle 1 and particle 2. Bob has access to particle 3 only. So he is at a distance, and Alice and Bob actually sharing this entangled state. So now, yeah, in the next step we will replace this product state in the next step we will replace this product state between 1 and 2 by some entangled states. Okay, so that is a very crucial step in this teleportation protocol. So this is the joint state of this whole problem, that is particle 1, 2 and 3. This is the joint state, and now we are going to what we are going to do, we are going to focus on this part of the wave function between the particle 1 and 2, like up up, up down, down up, down down. So we see that these indices 1 and 2. So the states we are going to focus on this part of the problem, that is we are focusing on the joint Hilbert space of particle 1 and 2, and these are the states, this up 1, up 2, up 1, down 2, down 1, up 2, down 1, down 2. These are the states which belongs to the joint Hilbert space of particle 1 and 2. So in the joint Hilbert space of this particle 1 and 2, we can have states like this: up up, we can have states like up 1, up 2, up 1, down 2, down 1, up 2, 2, and down 1, down 2, down 1. So we can easily see that these 4 states belongs to 2 qubit Hilbert space, and they all are orthogonal to each other, and they also form a complete set of orthonormal or orthogonal bases in this Hilbert space, that is in the Hilbert space of particle 1 and 2. So this is one choice of basis in this 4-dimensional Hilbert space, because it is 2 qubit Hilbert space of particle 1 and 2, and 2 qubit means 2 cross 2 4-dimensional Hilbert space, and we can have 4 orthogonal states or 4 orthogonal bases in this way. But this is not the only choice of basis in this 4-dimensional Hilbert space. If you have gone through my first lecture of this series, we have seen that there are other possibilities of, we can also have superposition of these states. So these are this is not the only choice of this orthogonal basis. We can construct 4 orthogonal bases. We can construct another 4 orthogonal states, which are basically superposition of these product states. So these are product states, and we can construct another set of 4 orthogonal bases in this way also. So we can have another set of 4 orthogonal states or orthogonal basis states in this 2 qubit Hilbert space. So I am writing it down, that another choice here, state like this: 1 by root 2, up 1, up 2, plus down 1, down 2. So this is a superposition of these 2 product state, up up and down down. So we construct another 4 orthogonal state, which are in a linear combination of these product states. So this is one of them. Another state we can have like this: 1 by root 2, up up, minus down down. Another choice will be third state, we take it as another choice we can have: 1 by root 2, up down, plus down up. So this state is a linear combination of these two states, up down and down up. So this is another superposition state, and lastly we can have another state: 1 by root 2, up down, minus down up. So we can have this another set of 4 orthogonal bases in this way. They are orthogonal to each other, one can easily check, and they are entangled states, and we have already discussed these states while we were discussing about the entanglement and Bell's inequality, and they are related to this Bell's inequality violation. So historically they are called the Bell state. These 4 states, they are called Bell states, okay, or sometimes we call Bell basis. As we already know that this is a 4-dimensional Hilbert space in this 2-qubit Hilbert space between particle 1 and 2, and there we can have this kind of product basis or product basis. These are 4 orthogonal bases in this Hilbert space. These are another 4 orthogonal bases in the same Hilbert space, but they are linear combination of this product state, and they are entangled, and which we call Bell state. So let us actually give the name of these states. So we name it as this first state, we call it as phi plus. So let us name these states. We call this state as phi plus and state between 1 and 2. So we write the indices are important. Phi plus 1 2, we call this phi plus 1 2. This one we call it as phi minus 1 2. This is phi minus 1 2, and this Bell state we call it as psi plus 1 2, this one, and this state we call it as psi minus 1 2. Okay, so these are 4 orthogonal Bell bases actually. So these are the Bell states, and these are the 4 orthogonal product states which are there in this expression. So we can easily see that this up down, down up and down states are here. So what we will do next, we will actually replace this basis. So we will transform, we will do some basis transformation. So as we know that this is a particular set of bases in this 4-dimensional Hilbert space, and this is another choice of 4 orthogonal bases in this same Hilbert space, and we know that there is some relationship. We can go from one set of bases to another set of bases, and that's what we are going to do, and we will replace this product basis in terms of this Bell basis, that is entangled basis. So we can easily see from here that if we add these 2 states, phi plus and phi minus, then we can write down this product state up as a linear combination of these Bell states phi plus and phi minus. If we subtract these 2 states, phi plus and phi minus, then we will have this down state. So this down will be also a linear combination of this phi plus and phi minus, but in this case down case, it will be phi plus minus phi minus combination. And this up down state we can actually write down this up down state as a linear combination of this psi plus and psi minus. So if we actually add these 2 states, we can easily see, just adding these 2 states, we can have this up down state. Up down state we can then write down it as a linear combination of the psi plus and psi minus, and also just in that case we will do psi plus minus psi minus, and then we will have this down up state as a linear combination of this psi plus and psi minus, psi plus minus psi minus. If we do that, we will have this down up states. So let us explicitly write down this product state in terms of these Bell states. So we just write it down here. So this up will be, this up state will be up 1 up 2. This product state we can write it as 1 by root 2 phi plus phi minus, and up down state, the second one, up down, and this product state we can write it down as a linear combination of these Bell states, up down, the combination of psi plus and psi minus. So let us write it down here, 1 by root 2 psi plus psi minus, and then what we have down up, this product state down up, we can write as a linear combination of psi plus and psi minus again, but there will be a minus sign over there. So it will be just like this, psi plus minus psi minus. And the last one, we have this down state, which will be this down state, down product state. We can write it down as a linear combination of this and this, but in this case we have to write it as phi plus minus phi minus. Okay, so this down state can be written as a linear combination of these Bell states as phi plus 1 2 minus phi minus 1 2. Okay, so what we have done, we have written down this product basis in terms of the linear combination of this Bell basis. So this is I am repeating it again. This is a particular choice of basis in this joint Hilbert space of particle 1 and 2. This is another choice of basis in the same Hilbert space, but they are in the product basis. We call them product states, and they are these basis is entangled basis, or they are all of them are entangled states. Okay, 4 orthogonal entangled state, here 4 orthogonal product states. Okay, now we have actually done this change of basis. So we have gone from one set of basis to another set of basis. So basically we have written down this product basis in terms of the Bell basis. So next what we will do, we will replace these expressions, that is this up down up down states for this particle 1 to here we will replace this up by this expression, and then this up down we will replace it by this expression, and down up this state here we will replace it by this state, and down we will replace this expression by this one. So let us do it and see. Let us do it and see what is the form taken. So let us do it and see the final expression of this psi 1 2 3, how it looks in terms of this replacement. Up to this we are actually doing nothing, we are just replacing these states between this particle 1 and 2 in terms of this Bell states actually. So let us do it, and then we will see that gradually we will understand that why we are going to this Bell basis to make this teleportation protocol successful. So let us now substitute these product states in this two particle Hilbert space 1 and 2, up down up down by these entangled basis. I mean we replace these product states in terms of as a linear combination of these Bell states. Then we have already shown that this up state can be written in as a linear combination of this phi plus and phi minus. So we just substitute that over here, and we just write down this final expression, I mean from here. Then this joint state of this particle 1 2 3, how it looks. So that will be equal to alpha by root 2, and this up state is up state we can write it as the linear combination of phi plus and phi minus. So that is 1 by root 2 phi plus phi minus 1 2, and then this state, and this state is there up 3 for the particle 3 at both sides. So I am writing this up 3 as it is, and the next term is plus alpha by root 2, and then this product state up down we will replace it by this Bell basis. So up down we can write, we have already seen up down can be written as a linear combination of psi plus and psi minus. So we have to add these two states. So that will be 1 by root 2. So we replace this up down state by this one, psi plus 1 2 plus psi minus 1 2, and this down 3 I am writing it as it is, plus this third term. In this third term we have this product state down up. So in this third term we have this product state down up. So that will be that we can write it as a combination of this and this, actually psi plus minus psi minus, that will give us this product state down up state. So we will replace this down up state over here, beta by root 2, and then this down up can be written as 1 by root 2 linear combination of the psi plus psi minus, but here it will be minus sign. So that will be psi plus minus psi minus, and then we have this up 3 over here, and then this last term is beta by root 2, and this down state, this product state, we can replace it by the linear combination of these two states, phi plus and phi minus. So if we subtract this and this, that will give me down state actually. So we just replace this down by this linear combination of Bell state
in this way 1 by root 2.
In this case it will be 5 plus minus 5 minus.
So in this case it will be 5 plus minus
5 minus 5 minus, and then there is this down 3 over there. So
I am writing it as it is, down
3. Now this is the final expression of this whole 3 qubit joint 3 qubit state. We have written it down after substituting actually this product basis between this particle 1 and 2 by the Bell basis, and we should, in this teleportation protocol, we should realize that this particle 1 and 2, they are accessible to Alice. Alice has access to these two particle 1 and 2, and Bob has access to particle 3 only, who is at a distance. So the purpose of Alice is to send this information about this particle 1, that is the state psi, to Bob. So Alice will do something over here, and then we will see that how she can actually send this information, quantum information about this qubit state psi to Bob. Even Alice don't know any information about the state psi, and she has only one copy of that state. So that we will see in the next part of the lecture. So this is the final state of this whole joint state of this particle 1, 2, 3. Now we will little bit simplify this state. So next what we will do, we will actually try to simplify this expression and see what happens. So let us now simplify this expression. We do some simple linear algebra. So this first term, let us focus on this first term, that is alpha by 2, alpha by 2, 5 plus 1 2, 5 plus 1 2, and then up 3, and then the second term will be alpha by 2, 5 minus up 3. So that is plus alpha by 2, 5 minus 1 2 of 3. Okay, then the next term will be alpha by 2 psi plus alpha by 2 psi plus 1 2 down 3 plus alpha by 2 psi minus alpha by 2 psi minus 1 2 down 3. Then this term beta by 2 psi plus up 3 plus, sorry, there is a minus sign over here, so this should be minus beta by 2 psi minus 1 2 up 3, and from this last line we have beta by 2 5 plus 1 2 down 3 minus beta by 2 5 minus 1 2 down 3. So this is, up to now we have obtained this final expression. Okay, up to now we have obtained the final expression for this joint state for this whole system 1 2 3. Okay, so we start from here, and we simplify this expression further. Okay, so we just simplify this expression over here. So we write it down, we start from here. So let us simplify this expression. So we see that 5 plus is here and 5 plus is here also. We can combine these two terms, this term and this term. Let us combine. So we can write it in this way, half. Okay, so this expression we are simplifying it here. This is equal to, combining this term and this term, we have half 5 plus 1 2, then we have here alpha up. So what we have, alpha up 3 from here, and from here it will be beta down 3 plus beta down 3. So this order we should not change. So this is just a linear algebra. So 5 plus 1 2 we are taking common, and it is multiplied with this state. There is a tensor product over here.
which we are not writing every time. So combining this term and this term, we have this. Now next we combine this term 5 minus here and this term. Okay, so let us combine these two terms, and combining these two we will have half 5 minus 1 2, yeah, we are taking common of this 5 minus term, 5 minus 1 2 state, and what is left, alpha up minus beta down. So this multiplied by alpha up 3 minus beta down 3, beta down 3. So these are the state belonging to the state of Bob's particle, the third particle actually. Okay, so this, from this term and this term we have already written half 5 minus alpha up minus beta down. Okay, next we combine next we combine another two terms which contain psi plus. Okay, so next we combine this term containing psi plus and this term. In both these terms psi plus is common, so let us write it down. Half psi plus 1 2 multiplied by what is there, alpha down. Okay, alpha down, and from here plus beta up 3. So this is also done. Terms containing psi plus state, psi plus 1 2. Now what is left, this one and this one. So here psi minus is common, so we combine these two terms, psi minus, so half psi minus 1 2 multiplied by alpha down minus beta up. So alpha down 3 minus alpha down 3 minus beta up 3 minus beta up 3. Okay, so now this is the final expression of this joint 3-qubit system, where now we have written it in a nice form, where these are the state for particle 1 and 2 multiplied by a state of particle 3 here. So next we will see that Alice will do some measurement in this basis, and then according to the results of the measurement, Bob's particle will be prepared in those 4 states, and then Alice will make a phone call. So that strategy I am going to explain in the next part. So up to now what we have done here, we have written down this joint state 1 2 psi 1 2 3 for this whole 3 particle 3 qubit system in this nice form, where these are this 5 plus 5 minus psi plus psi minus, they are the Bell states for this joint Hilbert space of these 2 particles 1 and 2, which Alice actually accessing, and these are the states, this alpha up plus beta down, or alpha up minus beta down, or alpha down plus beta up, alpha down minus beta up. So these are the states which belongs to the Hilbert space of this particle, this third particle. So you can we can think of a tensor product. Actually there is a tensor product over here, where these state belong, so these states 5 plus 5 minus psi plus psi minus, they belong to this 2 particle Hilbert space for particle 1 and 2, and these are the states on the right. They represent the 4 different states for particle 3 actually. So now next what Alice will do, because she has access to these 2 particles in her lab, so she will do a joint measurement in this Bell basis. So these are the 4 bases for this 4-dimensional system, that is 2 qubit system. So what Alice will do, Alice will make a measurement in this basis phi plus, phi minus, psi plus and psi minus. So, these are the 4 orthogonal states in this 4-dimensional Hilbert space. So, they construct a basis for some measurement, we call it Bell measurement. Okay. So, Alice will perform this measurement in this Bell basis, and if she, so when she does this measurement, so when Alice perform this Bell basis measurement, what she will actually obtain, she will obtain this result. So, now since Alice has access to this particle 1 and 2 on her lab, and she performs a projective measurement in the 2-qubit orthonormal Bell basis, that is in this basis phi plus, phi minus, psi plus, psi minus. So, when she does that measurement in Bell basis, what she will obtain? She will obtain one of the 4 Bell states. So, either she will obtain this phi plus or phi minus or psi plus or psi minus when she will make the measurement on these 2 particles in the Bell basis. Okay. And when she will obtain a particular result, for example, this phi plus with probability 1/4, because there are 4 possibilities for this Bell measurement on this particle 1 and 2, and she will obtain this result, this phi plus 1 2 with probability 1/4, and with equal probability 1/4 she can obtain this result also phi minus 1 2, and psi plus 1 2 again with probability 1/4, psi minus 1 2 again with probability 1/4. So, these are the possible outcomes for this Bell basis measurement for Alice's measurement on this 2-qubit, on this 2-qubit in this orthogonal Bell basis orthogonal measurement in the Bell basis. Okay. So, now say for example, Alice obtained the result phi plus with probability 1/4, then what will happen? The state will collapse to this part of the wave function. When she obtained this result phi plus 1 2, the state will collapse to this 3-qubit state will be collapsed, the 3-qubit state will collapse to this part of the wave function. So, this is the total wave function or the total state, and when she obtained this particular outcome for her Bell basis measurement, this phi plus 1 2, the joint state for this 3-qubit will be collapsed to this part of the wave function. So, from here one can easily see that Bob's particle will be collapsed to this alpha up plus beta down state. Okay. So, when Alice obtained this result phi plus 1 2 for her Bell basis measurement, Bob's particle, Alice knows that Bob's particle is now collapsed into this state alpha up plus beta down. Okay. So, I am writing it here. Under the condition when Alice obtained this result, Bob's particle, that is the third particle, particle 3, state of the particle 3 will be this state. Okay. So, I am writing it here alpha up 3 plus beta down 3. So, this will be the state for particle 3 when Alice obtained this result, that is phi plus for her Bell measurement, Bell basis measurement, and with probability 1/4, as I said that Alice will obtain this result phi minus, and under that situation, so when she obtained this result phi minus, joint state of this 3-qubit system will collapse to this part of the wave function, and under that situation, under that measurement outcome, Bob's particle, that is the state of particle 3 will become this one alpha up minus beta down 3. So, when Alice obtained this result phi minus for her Bell basis measurement, Bob's particle will be prepared in this state alpha up minus beta down 3, this state. And in another situation when Alice obtained this result, that is psi plus for her Bell basis measurement on particle 1 and 2 jointly she does. So, then if she obtain this result psi plus for her Bell basis measurement, then the joint state of this 3-qubit system will collapse into this part of the wave function, and from here it is clear that when she obtained this result psi plus, Bob's particle will be prepared into this state, alpha down plus beta up. So under this situation, for this third outcome, that is when the outcome is psi plus for the Bell basis measurement, Bob's particle will be prepared in this state, alpha down plus beta up, alpha down plus beta up. Okay, it is clear from here, alpha down plus beta up. And in the another situation, when because there is a probability of 1/4, with 1/4 probability Alice will obtain this result also, psi minus, for her Bell basis measurement, for joint measurement on these two particles 1 and 2. If she get this result psi minus, then the joint state of this 3 qubit system will collapse into this part of the wave function, and from here it is clear that when she obtain this result, Bob's particle will be prepared in this state, alpha down minus beta up, alpha down minus beta up. So Bob's particle will be prepared into this state. So these are the situation under which Bob's particle, this particle 3, will be prepared in either in this state or this state or this or this, when the outcomes are either phi plus or phi minus, psi or psi plus or psi minus, with equal probability 1/4. Under those various measurement outcomes, that four possibilities for Alice's measurement on her particle 1 and 2, that is the Bell basis measurement, she will get either phi plus, phi minus, or psi plus or psi minus, because she has access to this two particle and she can make this joint Bell basis measurement. And according to the measurement outcomes, Bob's particle will be prepared either into this state, this state, this state, or this state. Okay, so there are four possibilities out there. That is the four possibilities. Bob's particle will be prepared into these four states according to the four measurement outcomes of what Alice obtained for her Bell basis measurement. Okay, now let us recapitulate what was the original purpose of this teleportation protocol. The purpose was that this state Alice want to send it to Bob. Okay, and what was that state? Psi. Psi was, we remember that the state of this particle 1, which actually Alice wanted to send to Bob, that was alpha up plus beta down. Okay, so this 1, because this we named it as particle 1. So this, but the state is alpha up plus beta down. Okay, now we see that in this case, Bob's particle is already prepared into that state actually. Particle 3 is already prepared in this state, alpha up plus beta down. So when Alice obtained this measurement outcome, phi plus for her Bell basis measurement. So when Alice obtained this result, phi plus for her Bell basis measurement, Bob has to do nothing actually. So what Bob will do nothing, because so when Alice obtained this outcome phi plus, so Alice knows that Bob's particle is already prepared into this state, alpha up plus beta down, which is this state psi actually. So the teleportation of this state is already done actually. So the state is already prepared into this particle 3. So in that case, what Bob has to do? Bob has to do nothing. So Alice will inform that to Bob that please do nothing, because the state of your particle is already prepared into this state. So in that case, mathematically we say that we apply an identity operator on that state. Okay, so applying identity operator on that state means actually Bob has to do nothing. And in this situation, another situation, when Alice obtained this result phi minus, we see that Bob's particle is prepared into this state. Okay, Bob's particle is prepared into this state, and then Alice will actually, then under that situation when Alice obtained this result phi minus, so under that situation when Alice will obtain this result phi minus for her Bell basis measurement, what she will do, she will inform to Bob, she will make a phone call that you please just apply this unitary transformation on your qubit, this unitary transformation sigma z. So Alice will make a phone call to Bob to apply this unitary transformation to his qubit, so that the state will be transformed into this state. We know that sigma z this is an unitary sigma z is a unitary operator. When it will act on this state, what it will do? It will actually do this alpha up, and sigma z acting on down state gives us -1. So this will make it plus beta down. Okay. So we see that when Alice obtained this result phi minus, she will make a phone call to Bob to asking him to apply this unitary operator sigma z, so that Bob's particle will then be transformed. So this is a unitary transformation Bob has to apply to transform the state from this to this one, alpha up plus beta down. So in under that situation, we also see that this state is prepared on Bob's particle 3. Okay, and in this situation, in the third case, when Alice obtained this result psi plus, Alice knows that Bob's particle is prepared into this state. Okay, alpha down plus beta up. In that case, what Alice will do? Alice will make a phone call to Bob. So Alice will make a phone call to Bob and asking him to apply this particular unitary operator sigma x. Alice will ask Bob to apply this unitary operator sigma x on his particle, because his particle is prepared in this state. So when he will apply this unitary transformation sigma x, what it will actually do? It will transform this state to again into this state, because sigma x actually flips the spin. So it will become alpha up plus beta down. So we see that in that case also this state is now prepared into this particle 3. Okay. And in the last situation, when Alice obtained this result psi minus, in that case Alice knows that Bob's particle is prepared into this state. So then also Alice will make this phone call and ask Bob to apply some unitary transformation on his qubit. So that unitary transformation is a particular unitary transformation, which is this one, which is this sigma z sigma x. So what Bob will do? Bob will first apply sigma x on his particle and then sigma z. So effectively this is an unitary operator which is equal to I times sigma y. So basically this is a unitary operator which Bob has to apply to his particle to make the transformation from this state alpha down minus beta up. So after this unitary transformation, this state will also become this state alpha up plus beta down. Okay. So essentially what we see that for the teleportation protocol to be successful, that is the original motivation of Alice was to send this state psi from this place to a distant place to Bob. So Alice wanted to send this state psi to Bob, and that is now successfully Alice can do. So she will actually make this Bell basis measurement, and according to the measurement outcome, she will make a phone call to inform Bob that after her measurement outcomes, what she obtained according to the measurement result, she will actually, so according to the measurement outcome, Alice will ask Bob through this phone call that you must apply identity operator on your particle. That is, you do nothing in this case when Alice obtained this phi plus measurement outcome. So you just apply an identity. In that case, your state is prepared. Actually, your state is already prepared in particle 3. And in other situations, when Alice obtained this result phi minus, Alice will ask Bob to apply this unitary operator. So these are unitary operator. So local unitary operator Bob can apply on his particle 3. Okay, so this is an unitary operator sigma z. He can apply to his qubit to make this transformation from this state to this state, the original state what Alice wanted to send to Bob. Okay. So, and under this situation, under this third situation, when Alice obtained this psi plus, what she will do? She will actually inform to Bob that please apply this unitary transformation on your qubit. that is this sigma x on your qubit to make this transformation, because your qubit is prepared in this state, it is not this one. So you have to apply sigma x unitary operator to obtain this alpha up plus beta down. Okay, and in the last case, that is when in the fourth case, when Alice obtained this particular outcome for her Bell basis measurement psi minus 1 2, when she is making the measurement, a joint measurement on these two particles and getting the result measurement outcomes, and depending on the measurement outcomes she is making a phone call and asking Bob to make this 4 possible unitary transformation. Actually this is just a trivial identity. This is another one, another unitary transformation sigma z, this is the unitary transformation sigma x, and this is another unitary transformation which is I sigma y, and that can also be done by Bob. So he has to apply so that he will obtain that final outcome. That means his particle will be prepared into this state. So there are 4 possibilities, and so Alice has to send 2 bit of information after this Bell basis measurement. She has to send 2 bit of information. Why I am saying? Because there are 4 possible outcomes, 1 2 3 4. Okay, so Alice will make phone call. When Alice will make a phone call, she will have to send 2 bit of information for these 4 possible results, 4 possible outcomes. Okay, and that is she can encode this as 00 01 10 11. Yeah, these are classical information. So 4 possible classical information encoded in 2, so we say it 2 bit of information she needs to convey to Bob, so that to make this teleportation protocol successful. So when this outcome is obtained, phi plus is obtained, she will actually, through this phone call, she will send this information, this bit of information 00. When this measurement outcome, this Bell basis measurement outcome phi minus is obtained, Alice will send this bit of information, 2 bit of information 01, and in that case she will send this bit of information 10, and in this case this classical information. So Alice needs this 2 bit of classical bit of information through the phone call to Bob to make this teleportation protocol successful, because without this it cannot be done, because Bob actually doesn't know that what is the state of his particle. Only when Alice actually informed to Bob that you have to apply the identity operator or sigma z operator or sigma x operator or this I sigma y operator to get this state, that is this state on his particle, then only Bob can prepare this this state, and that also it is probabilistic, because Alice will obtain this result phi plus or phi minus or psi plus or psi minus with randomly. She will get this result with equal probability of 1/4, and when she get any particular measurement outcome, for example phi plus, then only she knows that Bob's particle is prepared into this state. So so Bob has to do nothing. Okay, and if she obtain this result phi minus with probability 1/4, then Alice knows that Bob's particle is prepared into this state. So Bob's particle is prepared into this state, but still now Bob doesn't know that. So Alice has to convey this information that you have to apply some unitary transformation sigma z on your particle. She will ask Bob that you apply this unitary transformation to your particle to get this state, this original state which she wanted to send. And in that case Alice will inform through this phone call. In this case Alice will inform to Bob through phone call that actually your particle 3 is prepared into this state. So you have to apply some unitary transformation I sigma y to your particle, so that this there will be this transformation to get this state. Okay, So, this is the quantum teleportation protocol which I explained it here. Let us now briefly talk about this no cloning theorem in quantum mechanics. As I promised in the beginning of my talk that I will discuss about this no cloning theorem in quantum mechanics. So, this theorem says that an arbitrary unknown quantum state psi cannot be copied, and the original paper was published with this title, a single quantum cannot be cloned. This was the original paper published by Wouters and Zurek. So, this is the reference of that no cloning theorem paper in published in Nature. The author's name W.K. Wouters and W.H. Zurek, published in Nature, volume 299 and page 802, 1982. Okay. So, we discuss a simple version of this no cloning theorem. So, the purpose of cloning is to copy an arbitrary quantum state psi. So, let us assume that there is a quantum cloning machine which can copy this state psi. So, it will make another copy. So, for example, we have a quantum cloning machine and this is the state which we want to copy, and like a Xerox machine we take another state B which we call the blank state. This is the state which we want to copy into this blank. So, this is the original state which we want to copy into this one. This is a blank copy, like a blank page in a Xerox machine. Okay. The purpose is that there is we assume that there is a universal quantum copy machine. It is an unitary operator. So, this unitary operator will act jointly on this state, and it will give us as an output, it will give us two copies of the original state. So, this is the state which we want to copy, and this is the blank page or blank copy. This is the original state and this is the blank state. This quantum cloning machine will act some unitary operator on this joint state of these two particles, and as an output we will have these two copies of this arbitrary quantum state psi. So, mathematically if we want to write down this quantum operation, so we have to write it in this way, that this unitary operator u acting on this input state. So, u acting on this psi and b. So, there is a tensor product because they are two different system, for example like a qubit register in a quantum computer. So, it is like some unitary gate acting on this joint system. So, psi and b, this is the input state, psi tensor product b, and u acting on this unitary operator acting on this input state. This is the input state. When it is acting on this, this will give us this state psi, two copies of psi. So, this will make psi. This is the purpose. So, we assume that there exists some unitary operator which actually will actually transform this state, this input state psi blank to two copies of the same state. So, this we call as equation 1. Okay. Now, since we are assuming an universal copy machine, so that this operation can be done for any arbitrary state. So, here this copy operation is done for this arbitrary this state psi. So, let us assume that it can copy another state, another arbitrary state phi. So, another arbitrary state phi. Okay, now I am changing the state, input state from psi to phi actually. So, for another state phi, it can also copy, because in a Xerox machine, like if it can copy a certificate, it can copy another document also in the same fashion. So, this copy machine should copy another state phi also. So, that will make two copy of that state. So, here it will be phi and phi. Okay. So, in that case the mathematical operation will be okay. So, this same copy machine will create so this same unitary operation, when it will act on phi b phi tensor product the blank state, it will give us 2 copies of that state phi. So in this case we'll get phi tensor product phi. Okay, so we write it as equation 2. So what we have assumed, that there exists a quantum cloning machine or some quantum unitary operator through which this operation is possible, and this operation is also possible. That means we take a blank copy on which we can copy a particular state psi as well as a particular arbitrary state phi, so that ultimately it will make 2 copies of those states. Okay. So from this equation 1 and 2 we can show that there is a contradiction arising, and that we will show in the next step here. So now what we will do, we take the inner product of these 2 equations. Okay. So taking the inner product of these 2 equations 1 and 2, we will obtain this one. So we take the Hermitian conjugate of the first one, so it will be bra psi bra b u dagger, and then we take the inner product with the second equation. So in the second equation we have u phi b, u phi b. Okay. On the right hand side we have the Hermitian conjugate of this will be psi bra psi bra psi. On the right hand side we will have bra psi tensor product bra psi, and we have to take the inner product with this one on the right hand side, phi tensor product phi. Okay. So this implies that now u is an unitary, this is a unitary operator, u is unitary operator. So this cloning operation, as I mentioned, because it is unitary, u dagger u is identity for an unitary operator. For a unitary operator, u dagger u is identity. So that will be I, and this bra psi and Kate phi, they are in the same Hilbert space for the first particle, and these are the state for the second particle, right. So this will inner product will we have to do for the first particle, so that will give us bra psi Kate phi, and this is unit identity operator, so there is nothing, and this bra b Kate b is there, this blank state. Okay. So the left hand side is done. On the right hand side what we have is, so we have to do the inner product in the same Hilbert space, particle 1 bra psi Kate phi, and for the second Hilbert space now we have bra psi Kate phi, again bra psi Kate phi. So finally what we have on the left hand side, now this is a normalized state for the blank copy for this particle. Okay. So this is 1, this bra b Kate b, that is 1 because they are normalized state. So on the left hand side then we have bra psi Kate phi, and on the right hand side we have this bra psi Kate phi multiplied by bra psi Kate phi, so bra psi Kate phi square. Okay. So now this equation, so from this equation what we can say, this equation will be satisfied only under the condition, under this condition this equation will be satisfied. First case is that when Kate psi is equal to Kate phi, Kate psi is equal to Kate phi. So when Kate psi is equal to Kate phi, we can see that this will be 1, and on this side also it will be 1. So this equation will be satisfied. Another situation, in another situation this equation can be satisfied, that is the second case when this Kate psi is orthogonal to Kate phi. So when Kate psi is orthogonal to Kate phi, that means this inner product is 0. So when this inner product will be 0, then also this equation will be satisfied. So what is the physical meaning of that? The physical meaning of that is that when psi and phi they are the same state, that means that we cannot actually take another state phi. So this quantum cloning operation cannot be done for 2 different state, actually we call them a non-orthogonal state, because if they are orthogonal, then also this cloning operation is possible. So if we have, for example, the task is to copy between psi and psi orthogonal, then it is possible to make this operation, because we can measure in this orthogonal basis and we can know the state, and that's why this copy is that's why this quantum cloning will be possible when this psi and phi, they are orthogonal under that situation, or they are the same means we cannot copy two different state under the same unitary operation. So but if I give you 0 and another state, for example 0 plus 1, so I tell you that I have given either 0 or this state. So is it possible to make a device which can faithfully copy these two non-orthogonal state? Then it is not possible. I mean, deterministically it is not possible, but probabilistically we can do that using POVM. Okay, the moral of the story for this no cloning theorem is that two arbitrary non-orthogonal state cannot be copied by a unitary, by some universal quantum cloning operation or unitary operation. And so yeah, this is basically the statement. An arbitrary quantum state which we have just one copy of it, we have just one copy of that state, then in that case we cannot make a device through which we can actually make multiple copies of it. That is the statement of no cloning theorem. But if we supply orthogonal states, then it is possible, because we can distinguish the orthogonal state by some measurement. Then by doing that measurement we can know the state, and if we know the state we can copy that. But if you don't know the state and we supply two non-orthogonal state like this, psi and phi, arbitrary two non-orthogonal state psi and phi, then we show here that it gives us a contradiction, because this equation will not be satisfied in that case when psi and phi has some finite inner product value, that means they are either not that is they are not they are neither orthogonal nor this same. So when psi and phi, they are two different state, non-orthogonal state, in that case this equation will not be satisfied. Okay, so that means we get a contradiction over here, and through which we can say that an arbitrary quantum state cannot be cloned or copied by some universal cloning operation if we have just one copy of that state. Thanks for watching. If this is the first time you are visiting my channel, please don't forget to subscribe it and tap the bell icon to get notified for my new videos. Please comment below. Your thoughts and suggestions would be greatly appreciated.